All right, in this video we're going to do a quick review of electron configurations and atomic structure. And we're going to start by distinguishing between the Bohr model and the quantum model. The Bohr model of the atom is, of course, the one we're first introduced to when we draw Bohr model diagrams. And it's a simple shell model, so it's only going to account for different energy levels, and it's not going to account for subshells or orbitals. And even though it's only partially correct model, it's still a really helpful one to rely on because we can think about valence electrons versus core electrons with just the Bohr model. The Bohr model worked well to explain the hydrogen atom when Niels Bohr studied the hydrogen atom. The problem is it didn't apply to other heavier elements quite as easily. And in order to account for the data from other heavier elements, a more sophisticated model was developed which incorporated subshells. But this image is a really helpful one to refer back to and think of because it reminds us that everything we know about the internal structure of atoms, or I should say electron behavior and electron configuration, comes from the light which is emitted when electrons move. And we'll study light a little bit more and learn about that in a different video or a different review. But of course, if there's a large jump in energy that's occurring, such as when the electrons are jumping from the fourth shell down to the first, then a high energy wavelength of light is going to be emitted. And the relationship between that energy difference and this wavelength of light is going to be related by Planck's constant. However, if a relatively small change in energy is taking place, for instance, between the second shell and the first, then the light that's associated with that energy jump is going to be a lower energy of light since that's a smaller change in energy. And very, very small changes in energy, like this one over here, is going to correspond to a much lower wavelength of light. And that's why we get different colors of light associated with flame tests or spectral tubes and other phenomenon, some of them infrared, some of them ultraviolet. So everything that we know about electron behavior really comes from the light that is emitted. So we'll need to review our understanding of light a little bit in order to dive into that. The purpose of this video, though, is really to just talk about electron configurations. And the electron configurations we're going to be discussing, of course, refer to sublevels, not just the energy levels of the Bohr diagram, but subshells like S, P, D, and F subshells. And the shortcoming of the Bohr model really is that it is sometimes called the planetary model, and it kind of imagined electrons like planets orbiting the sun. And while that's kind of an elegant analogy, it falls short of describing electron behavior. Electron behavior is really more akin to that of a wave. And a wave function is a much more complex thing to model than an orbiting object. But essentially, the model has gone from electrons orbit the nucleus at a fixed distance to electrons have a particular energy that is associated with a wave pattern. So the quantum model describes a quantity of energy that an electron has when it's in a particular orbital. So we're going to go from a really simple model of an electron as an object or a particle to a model of an electron as a probability wave. And that's a tricky thing. It is much harder to think of electrons as wave functions than it is to think of them as particles. So we're sometimes still going to use Bohr's simplified model, but you might remember that the quantum model uses this understanding of orbitals, and an orbital is not an orbit. An orbital is a region of three-dimensional space where an electron is likely to be found. So that's an important concept. You can see these are some of the higher leveled orbitals like D and F orbitals that are shown here. Just remember that an orbital is a probability map or a probability density distribution. So where you see these colored balloon-looking regions shown, that's just a region where there's a high probability of finding an electron in three-dimensional space. And the origin of these axes is the nucleus. And you can see in all of these, the probability of finding an electron at the nucleus is zero. All of these shapes kind of taper out to a node at the origin, and that's because that's where the nucleus is, and electrons don't exist at the nucleus. So let's review electron configurations and how to write them. What's called the Aufbau Principle, which is the German word for building up, refers to the fact that electrons are going to occupy the lowest energy state they possibly can, but there's a limit to how many low energy states are available, or low energy orbitals are available. We're going to describe the location of electrons in an atom using 4 quantum numbers. And the good news is we don't need to actually use the quantum number system in AP chemistry to remember these. You don't even need to know these letters, which correspond to the quantity symbol for each of these quantities. But we should know that an electron's location needs to be specified as a particular shell, like n equals 1, n equals 2, or n equals 3. And we will use the letter n to describe that, but also by the subshell, like is it S, P, D, or F. The orbital, because remember there's only one S subshell, but there are there's only one S orbital, and there are 3 p orbitals in the p subshell. And so we're going to need to describe the orbital, and finally the spin, which we often do with orbital diagrams. Let's go through these each one at a time. The principal quantum number n is just going to refer to the shell. So this is just like the Bohr model, is n equal 1 or n equal 2, n equal 3, and that corresponds to distance from the nucleus. So the n equals 4 shell is farther away, and it's also bigger. So that is the size of the orbital. As n increases, so does energy. So that means that the first shell is the lowest energy shell. Electrons in that shell are at the lowest energy available. The farther away from the nucleus they get, that's a higher energy value. So the 2s orbital is a much higher energy level than the 1s. The secondary quantum number is just going to refer to the subshell. And of course, the subshells are S, P, D, or F. Now, every shell has n subshells. So the first shell only has an S. The second shell has an S and a P. The third shell has D subshells in it as well, and it's only when we get to the fourth shell we start seeing F subshells. And an S subshell is, of course, a lower energy than a P, which is a lower energy than a D, and so on. We can think about the shapes of these subshells. An S subshell you could think of as spherical. You could think of the P subshell as polar, although that's not what these letters stand for. It is true that subshells have different shapes, which are helpful to think about sometimes. The next level of an electron's address is the orbital that it's in, and remember that a p subshell, for instance, has 3 orbitals, a d subshell has 5 orbitals, and an f subshell has 7. So the orbital is the actual 3D orientation in space that 2 electrons will have in when they're assigned to a particular orbital. So here's a nice summary. This is a picture of an s orbital. Every s subshell only has 1 orbital. 2 electrons can reside there. Here are pictures of the 3 orbitals of the p subshell. And you can see each of these add up to the total number of electrons that can be in a p subshell, which is 6. 2 in this orbital, which would be called the px, this one, which is called the py, and this one, the pz. You don't need to worry about naming orbitals within subshells, but you should know that there are 3 orbitals in a p subshell and 5 orbitals in a d subshell. And notice that the use of the language is very important there. An orbital is not the same thing as a subshell. You can refer to a subshell as a sublevel or as a subshell, but an orbital is a region of space that an electron can occupy, and only 2 electrons can occupy a particular orbital. There's the 3 p orbitals. I like this diagram because it really illustrates that this is a probability density distribution. And while it might look like there's a lot of dots there, that is just sort of the blur of 2 electrons in that region of space. So remember, there can only be 2 electrons in an orbital. Here's the 5 different types of d orbitals. And these are very strange wave function shapes, right? Very sophisticated math that Schrodinger needed to use to model these. The last level of an electron's address is the spin. And just remember, there's two electrons in an orbital. One of them has a spin which is called up, and the other one has a spin which is called down. The numeric values of positive 1/2 and negative 1/2 don't matter to us. The fact that this has the quantity symbol ms doesn't matter to us. When we're drawing electron configuration diagrams, we want to think about the fact that every orbital is going to have two electrons in it, and they're going to be represented by an up arrow and a down arrow when we look at those electron configuration diagrams. So let's talk about electron configurations now, and we're going to want to think of the periodic table as having these different regions. This is a really helpful way to look at the periodic table because each region that's colored differently here corresponds to a different subshell or sublevel being filled. So let's wrap up by just discussing the order in which we're going to be filling electrons in an atom. And we are going to start with the lowest energy electron vacancies first. So that's why we start with 1s and then 2s. And as we're going across the 2p, for instance, or across the 3d, remember that electrons will remain unpaired until there's no other vacancies in that subshell available. So that is called Hund's rule. And the two things we want to keep in mind that electrons are added to the lowest energy level available, but also that electrons will not pair in orbitals unless there's no other subshell vacancies available. So that's called Hund's rule, and we just want to always make sure we maximize unpaired electrons in a particular subshell. And there's some consequences for unpaired electrons that we'll talk about a little bit later. So last point here is a reminder that we can always abbreviate an electron configuration by writing the noble gas that corresponds to its core electron configuration in brackets, and then continuing with the valence electron configuration from there. So this is an example that chlorine could be written as 1s2, 2s2, 2p6, 3s2, 3p5, or it could be written like this. That's an abbreviated configuration.